All right, now that we understand this idea of sort of the structural and architectural elements in NumPy arrays, like the dimensionality and the shape and the size and the different data types, and sort of the architectural sort of attributes of these different arrays, now we get to talk about some of the really cool things that NumPy can actually do for you. And one of the biggest parts of NumPy is that it creates efficiency where Python has inefficiency. Okay, so I mentioned previously that lists and Python in and of itself is a very inefficient programming language. So iterating through a list, loops in Python are very, very, very slow. And that inefficiency in looping can really slow things down when we do data analytics, because in data analytics, a lot of times we're finding mean, medians, modes, standard deviations, maybe doing some linear regression. And all of those require looping through all the different values in your data set. Okay, so if you have to loop through every value in your data set to do data analytics, and looping is slow in Python, then that means Python is very inefficient and it's very hard to use in its sort of native sense. Okay, so in NumPy, they created these things called universal functions. We also call them ufuncs. And the ufuncs actually they use sort of this idea of vectorization, and it creates extremely efficient processing for these things that in Python vanilla would be very, very, very time intensive. Okay, so again, Python's default implementation of looping, called CPython, does some operations very slowly. I got to be honest, it does most operations very slowly. And looping is no exception. Looping in Python is extremely slow, okay? So we need to do something to make a faster loop in order to make Python more efficient. So let's take an example here real quick, okay? So this function, compute reciprocals, we're going to pass in a NumPy array called values, okay? We're going to create an output array, np.empty at the length of the values, and then we're, for I in range, the length of values, we're going to iterate through every single element in values. We're going to add into output index I 1 divided by values at I. Okay, so we're just basically finding the reciprocal of every single value in the values array. Okay, and then you return that output. Okay, so you can see the call, values equals np.random randint. So we're creating a random integer, 1 to 10, size of 5. Okay, and then they compute the reciprocals here. So essentially you end up with reciprocal, 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 so on and so forth. Okay, now the function itself is rather inconsequential. What's interesting is the time it takes to run it. Okay, so they created a big old huge array. Okay, so from 1 to 100, size of, what is that, 1 million? Okay, and then they compute the reciprocals of that. Took 2.63 seconds to compute these millions of operations. Okay, to go through each one of these, it took 2.63 seconds. Now again, for us in human terms, that seems relatively fast, but in NumPy, when we use ufuncs and vectorized operations, we could do the same thing where we create this big array with 1 million elements in it. We can just do 1.0 divided by big array, which will actually map 1 divided by the first element, 1 divided by the second element, 1 divided by the third, fourth, blah, 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 blah. And it'll do all of those calculations that we did in 2.63 seconds in 2.9 milliseconds. 2.9 milliseconds. So it is absolutely ridiculous how much faster this vectorized operationality of NumPy is. And that's why when you're doing big data analytics, you need to be using NumPy. Otherwise, it's going to be a very slow, very miserable experience. Okay, so again, it's much, much, much faster, much more efficient. It's also extremely flexible because what we can do now is we can use mathematical operations and mathematical operators, sort of like the divided symbol, the multiplication symbol, exponent, plus, minus. We can pile those all together and use entire arrays as variables. So for instance, I can create x as this np.arange 9, so that'll count from 0, 1, 2, 3, 4, 5, 6, 7, 8. We can reshape that into a 3 by 3. And then I can go 2 to the 0, 2, and then I can iterate through each of these and do the 2 to the exponent x, and it'll map across all of these. So it'd be 2 to the exponent 0, 2 to the exponent 1, 2 to the exponent 2, 2 to the exponent 3, 2 to the exponent 4, 2 to the exponent 5, 2 to the exponent 6, 2 to the exponent 7, 2 to the exponent 8. Okay, and it maps this function across all of the values inside of that particular array, which is really, really cool because previously we'd have to do a for loop to be able to do that. And we understand that for loops in Python are very slow, which means all of a sudden we sort of hit this molasses, this syrup that slows all our operations down. Now, with this vectorized operationality in NumPy, we can do it much, much faster. Plus, it's very intuitive to think about. So, for instance, let's imagine that this x equals np.arange 4 is actually not an array; it's just a value. So, say x equals 6. Okay, so for us, it's very easy to imagine these print statements. So this would be x equals 6, this would be x equals 6 plus 5, this would be x equals 6 minus 5, 6 times 2, 6 divided by 2, 6 divided by 2 integer, negative 6, 6 to the 6 squared, and 6 mod 2. Like, we can visualize that very easily. But what's cool about the ufuncs is this will map this operation across all of the elements inside of that particular list. So obviously arange 4 is going to go 0, 1, 2, 3. Okay, so we can see that x is 0, 1, 2, 3. Okay, we can offset by 5. So 0 plus 5 is 5, 1 plus 5 is 6, 2 plus 5 is 7, 3 plus 5 is 8. We can offset by negative 5. Okay, so 0 minus 5 is negative 5, 1 minus 5 is negative 4, 2 minus 5, negative 3, 3 minus 5, negative 2. We can do this, we can square each, 0 times 0, 0 times 0 is 0, 1 times 1, sorry, we're doing squared. 0 squared, 0, 1 squared, 2 squared, 3 squared, so on and so forth. Okay, and we can also do the division. We can do the integer division. So obviously float division is going to give you decimals, and then integer division is just going to truncate. Okay, so this would be 0.5, so it's going to truncate to 0. This would be 1, so it truncate to 1. This is 1.5, so it truncates to 1, so on and so forth. Okay, so we just sort of map this operation across every value inside of that particular array. Now, what's cool about this is we can actually build complex functions that would definitely work on a variable, but now work on the entire array, which is cool because you can modify big data sets by sort of known equations very, very quickly using the universal functionality of NumPy. Okay, which again, very, 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 very interesting, very, very cool. Now, NumPy also offers trigonometric functions. Okay, so again, we're just going to map the trigonometric function across all the values inside of the array. Okay, so I get the sines of all the elements in the array, the cosines of all the elements, or the tangents of all the elements, and you can see those down there. You can also do the same thing with exponents logarithmics. Okay, so I can do exponents here, and I can do just the power, so this would be to the third, so on and so forth across all the elements. I can do it with logarithmic stuff. So I can just do logarithmic. I can do log base 2, log base 10, and get all the answers I want across the entire array. Okay, so it has really, really cool stuff. Now, as you noticed, I think in an earlier video, I made a very, very large array and tried to output it onto the console. Okay, so it's important sometimes to be able to specify sort of where everything's going to go, how it's going to be in there if it's a very large array. Okay, so again, for large calculations, sometimes useful to be able to specify the array where the result is going to be stored. Okay, so we see here we have this np.arange. It's going to create something with values. Then we're going to create this np.empty. Okay, so the empty means it's just going to be a size of 5. But it'll just be empty. Everything is going to be null. Okay, so then what I can do is I can actually np.multiply. So I can multiply all the values in here by 10 and push that out into my empty array here. Okay, so basically what you're saying is y is my destination, x is my source, and then I'm going to multiply every element in x by 10 and save that in y. Okay, is what you can see. Okay, so 0 times 10 is 0. 1 times 10, 10. 2 times 10, 20, 3 times 10, 30, 4 times 10, 40, so on and so forth. Okay, you do the same thing with np.power, right? And you can actually create a new one, a new output array just like this as well. Okay, so I create a bunch of zeros, and we're doing to the power, right? 2 to this power is what we're doing, and then we create this out.y where we're going to jump by 2's. Okay, so you can see 1, 0, 2, 0, 4, 0, 8, 0, 16, 0, so on and so forth. Okay, so you can sort of specify the output on that. Okay, now we also have some other really cool things that we can do, like an outer product, which again is vectorized and it computes very, very, very fast. So it can be really, really, really good for what we call dynamic programming or triangulation, which is also a really, really neat way to solve some of the problems that you might be asked to solve in Cyber 180. Okay, so I would encourage you to just experiment with a lot of these functions on your own time, mess around with them, do the trigonometric stuff, create some different mathematical equations that you're pushing across entire arrays. Practice, 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 and then you should be pretty well set for understanding how you can actually use the universal functions. All right, so we're going to take a quick break. We'll be right back.